Hello everybody. Today we're going to talk about a way of evaluating limits of functions when you wind up with a strange answer by direct substitution. You wind up with something called an indeterminate form. It's a pretty easy lesson, but let's go through a couple of scenarios here just so you can be prepared for any possibility that comes up. All right, so you're going to need to know your differentiation rules, obviously the meaning of this indeterminate form, and then finally this limit property that says that if you have a fraction and the numerator is a constant and the denominator is getting larger and larger and larger, the value goes to 0. So just to kind of recap here, I'm not going to go through all of them, but I will put up on the slides here the ones that you should have learned already. You could always pause the video if you need this as a reference, but here are the big four: the power rule, product rule, quotient rule, and chain rule. And again, you could always pause the video if you want. I'm not going to go through them individually. Here are the rules for exponential functions and logarithmic functions. When you want to differentiate them, you should have learned these. You should have learned the derivatives of the 6 basic trigonometric functions and the derivatives of their inverses by now. Right? There's other things in there as well that you might have picked up along the way, but those are the big differentiation rules that you're supposed to have committed to memory in your toolbox to be able to handle some of these derivative application problems. The second thing is the meaning of indeterminate forms. Now, generally, when you have a fraction and the numerator is not equal to 0, but the denominator is, we call that undefined. But there's a special case. What happens if both the numerator and the denominator are equal to 0? That's called an indeterminate form, not undefined. Undefined is only the denominator equal to 0. And yes, technically this is not defined either, but it really is a symptom of a situation where you might be able to still work with the fraction. Indeterminate form. Indeterminate just means you haven't determined yet what it is. Right? So there's more work to be done. Now, 0 over 0 is one of them, infinity over infinity, or negative infinity over positive infinity. Any combination of infinity in a numerator or denominator is considered an indeterminate form. And for the rule that we're going to look at today, L'Hopital's rule, right? The rule works wonderfully, but only when you have one of the two indeterminate forms, 0 over 0 or infinity over infinity. There's actually several other types of indeterminate forms: 0 to a 0 power, 1 to the infinite power, infinity minus infinity. All these things are indeterminate forms, and they could still potentially work with L'Hopital's rule, but you have to rework them. You have to rewrite them in the form of 0 over 0 or infinity over infinity if it's possible to do that, right, before you can apply L'Hopital's rule. And the last thing was just that limit property I spoke about earlier. And again, this is really easy to demonstrate. Imagine you had 1 over 2, and now just look at your denominator getting bigger and bigger and bigger as your numerator remains constant. It doesn't have to be 1, it could be any constant, positive or negative. But if your denominator is getting bigger or bigger or bigger, the overall value of the fraction is going to 0. And that's a pretty famous limit property here. All right, so let's get into it. Here's the French spelling of this. You're going to see it both ways. I know it's a little confusing, but in France, they leave the S out between the O and the P. It's pronounced L'Hopital. L'Hopital's rule. And you'll notice in parentheses there it says Bernoulli's rule. I'll tell you a quick story about that in a moment. But that's the French pronunciation. We have, as they say, anglicized it, and we've given it an English spelling. So you're going to see it both ways here. Right? In our textbooks, it'll usually have the S. It does not say hospital. It is silent. It's still pronounced L'Hopital. L'Hopital's rule. And here's the rule. Right? If you have a limit of a function over another function, limit of f of x over g of x, as x is approaching some number, a, and when you do the substitution, you wind up with an indeterminate form. You get 0 over 0 or infinity over infinity. Then L'Hopital's rule says instead of doing the limit of f of x over g of x, you can take the derivative of the numerator and make that your new numerator, and the derivative of the denominator and make that your new denominator, and then substitute in the x value that you're approaching. So as you can see here in the blue font, it winds up being equal to f prime of a over g prime of a. And you're going to see there are going to be examples where you do this, you wind up with a first derivative over a first derivative, and when you substitute in the x value you're approaching, you still get an indeterminate form. And the beauty of this rule is that you can actually apply it again. You can do a second derivative over a second derivative. The main thing to be careful for in these scenarios here, let me change the color of this, is that you don't apply the quotient rule for this. If you're doing the limit of a quotient, that's not the derivative of a quotient. So you're not going to use the quotient rule here. Be real careful about what you're being asked. It's when you have a limit of a quotient and you wind up with an indeterminate form by direct substitution that this rule will work. Now, just quickly to give proper credit where credit is due, L'Hopital, there he is right there, handsome guy, huh? L'Hopital was a student of Bernoulli. Bernoulli taught him calculus, right? And it's actually been verified after the fact now that Bernoulli derived this rule that we call L'Hopital's rule and taught it to L'Hopital, and then L'Hopital published a textbook that included the rule, and everyone gave L'Hopital credit for it. And that was not too happy a day for Bernoulli there, and there's a little French from Bernoulli for L'Hopital. Anyway, now it's been known that Bernoulli actually came up with this, but we still call it L'Hopital's rule because everyone likes saying L'Hopital. All right, here we go. We're going to try to apply it. If we take this example, by the way, this is all on your worksheet, so you don't need to write this on separate paper. If we take this example and we use direct substitution, we get 0 in the numerator, 0 in the denominator. We get this indeterminate form situation. So what we do is we write a new fraction. Take the derivative of the numerator, which would just be 1, the derivative of the denominator, which would be that 9x squared minus 12x plus 1, and we write a new fraction with the derivative of the numerator over the derivative of the denominator, and substitute the x value that we're approaching, right? That's x equals 2, into the derivatives over themselves there, and we wind up with 1 over 13. So you actually go from an indeterminate answer to a specific value. You have an expected y value of 1 over 13 as x gets closer and closer to 2 from either the left or the right side. Okay, there you go. All right, so here's another one here. Famous kind of trig example. You guys probably learned the special trig limits where you have sine of x over x as x is approaching 0. That limit is equal to 1. But L'Hopital's rule allows you to actually come up with that and have a justification for it instead of just memorizing it and applying it. If I do direct substitution, again, indeterminate form, we get 0 over 0. But if you take the derivative of the numerator and the derivative of the denominator and create a new fraction from that, derivative over derivative, and then substitute in x equals 0, indeterminate form goes away, and you're left with 6. Right? Calc students love this rule because it's so easy to use, and it takes something that could be incredibly difficult and just shortens it down to a 10-second question. We love it when that happens. All right, here's another one. If I did direct substitution over here, again, I'd wind up with 0 over 0, indeterminate form. I'm going to ask you to pay special attention to this one because we're going to have to do L'Hopital's rule more than once. All right, so if I do the derivative of the numerator, I get sine of x. Derivative of the denominator gives me 2x. I write my fraction with derivative over derivative, and I substitute the x value I'm approaching, in this case 0, into there. And I get 0 over 0 again. I get an indeterminate form again. So now I'm going to redo L'Hopital's rule, but I'm now taking the limit as x approaches 0 of the first derivative over the first derivative, sine of x over 2x. So I'm going to reapply. Now I take the derivative of sine of x. I get cosine. The derivative of 2x gives me 2. I make a fraction again with that. And now when I substitute in, no more indeterminate form. I get 1/2 as my answer, and I'm good to go. Now, you can apply L'Hopital's rule several times. It doesn't have to be once or twice or whatever. It could be multiple times that you do it. You're going to tell right away, though, depending upon what forms your derivatives are in, whether or not it's going to work for you. This works really well when you have a polynomial over a polynomial, or one part of your fraction is a polynomial and eventually its derivative is going to get down to a constant. Then you know doing it multiple times will probably help you out. All right, here's a last one here. This is unique because we're now having an x value approaching infinity. Of course, infinity is a real number, so you can't substitute it in. So we simulate substituting it in by just putting in larger and larger values. We look at the behavior of the numerator and the denominator as we substitute in larger and larger real number values of x. And in this case, if we did that, the numerator is going to get bigger, the denominator is going to get bigger. We wind up with the indeterminate form of infinity over infinity. Now I'm going to apply L'Hopital's rule here, but I want to show you with these x approaching infinity examples, there's an even shorter way to do it than L'Hopital's rule. But let's finish this up here. All right, so I would do the derivative of the numerator over the derivative of the denominator. And when I substitute in larger and larger values of x here, I still get infinity over infinity. The numerator keeps getting bigger, denominator keeps getting bigger. So I apply L'Hopital's rule a second time. Derivative of 4x would be 4. The derivative of 2e to the 2x would be 4 times e to the 2x power. And then, when I substitute in there, I wind up with 4 over infinity. And if you remember back at the beginning of the video here, the third thing that I said you needed to know for today was that limit property that said if you have a constant numerator and your denominator is getting bigger and bigger and bigger, the expected value of that fraction goes to 0. So by L'Hopital's rule applied twice here, and by that property, we can say the limit of this is equal to 0. Now I mentioned there's another way of handling things like this when you're doing limits as x approaches infinity. It has to do with how fast the numerator and the denominator grow as x gets larger and larger. And I'm going to give you a real kind of simple overview of this right now, but you'll look at this a little bit later in the year as well. If you think of your numerator as f of x and your denominator as g of x, then there's really 3 possibilities here as x approaches infinity. If the numerator grows faster than g, because bigger, larger than at a quicker pace than g does, then the limit doesn't exist. If your denominator grows faster at a faster rate than the numerator does, then the limit will be 0. And if they grow at the same rate, then the limit is going to be the ratio of your leading coefficients. Now that's going to be the coefficient of the most powerful term in the numerator, the one that grows the fastest, and the leading coefficient in the denominator, same thing, it's the coefficient of the most powerful term in the denominator. And one last warning for you guys, one more time with this, because you're dealing with fractions and limits here, do not confuse the derivative of a quotient as a L'Hopital's rule application. It's not. L'Hopital's rule is when you're taking the limit of a quotient and you wind up with an indeterminate form. This is asking for the derivative of this, so you got to go back and use that quotient rule. You may have learned the memory device, low d high minus high d low over low squared, but either way, right, you would put the parts in there, maybe clean it up a little bit, and that would be the answer here. It's not a L'Hopital's rule scenario. So for homework and the rest of class, obviously finish the questions on the sheet. Try direct substitution first, always, with limit questions. See if you get an indeterminate form. If you do, apply L'Hopital's rule. If you don't, then substitution will work, and you just go with the substitution. Right? If you have any questions, you can find me in the building or email me, and have a great weekend, everybody. So long.